You've probably heard somebody refer to a really difficult, onerous task as the heavy lifting. Or maybe when someone else tells you that you have to do hard work on your own, they'll say, you can't have somebody else do your push-ups for you. So yeah, often when we're talking about hard work that we just don't want to do, we use metaphors that involve the skeletal muscles. And yeah, that's their reputation. They're what you use to perform all of the necessary but sometimes unpleasant brute force exertions that life requires of us. But they do a lot more than just heavy lifting. Your skeletal muscles, 640 in all, come in all different shapes and sizes, from the longest, the sartorius in your upper thigh, to the biggest, the gluteus maximus in your butt, to the tiniest, the stapedius in your middle ear, which I've been doing my best to work out lately, but I just can't get any definition. These organs are capable of a whole range of power and duration, as well as surprising and delicate subtlety. The same muscles you might use to pluck an eyebrow, or catch a firefly, or cuddle a kitten, can in other circumstances crush cans, or punch holes in walls, or do a bunch of push-ups. Which, by the way, are not really a thing. And she's gonna prove it. That's right, I'm gonna have somebody do my push-ups for me. Now, when you look at how the muscular system moves, you gotta keep two things in mind. First, muscles never push, they always pull. Now, how can that be, since Claire here is obviously pushing herself up? Well, remember that most skeletal muscles extend over joints to connect to at least two different bones. That's why they're skeletal. When a muscle contracts, the bone that moves is called the muscle's insertion point, and the muscle brings the insertion closer to the bone that doesn't move, or at least moves less, and that's called the muscle's origin. And that movement is always a pull, with the insertion bone being drawn toward the origin bone. And when you think about it, it has to be this way. Muscles can't, like, extend themselves beyond their resting state to push a bone away from it. So even though Claire's pushing herself up off the ground in an exercise we call push-ups, her muscles are actually pulling their insertions toward their origins. When she pushes herself up, her pectoralis major is contracting, pulling its insertion point, which in this case is the top of her humerus, toward the immobile origin, which is her sternum. Every single movement that your skeleton makes uses the very same principle, whether you're hammering on an anvil or lifting your pinky to sip a cup of tea. So that's the first thing. The second big thing to remember about skeletal muscles is that whatever one muscle does, another muscle can undo. You can generally classify skeletal muscles into 4 functional groups depending on the movement being performed. For example, the muscles that are mainly responsible for producing a certain movement are called that motion's prime movers, or agonist muscles. So when Claire does jumping jacks, she's using those pectorals in her chest and latissimus dorsi on her back to adduct her arms back down to her sides. Put another way, those are her prime mover muscles for adduction. At the same time, there are antagonist muscles that are working in reverse of that particular movement by staying relaxed or stretching or contracting just enough to keep those prime movers from overextending. So in this case, the antagonists of the jumping jacks would include the deltoids on top of her shoulders, which among other things help her slow down her arms so that she doesn't slap her thighs too hard. But when it's time to start abducting her arms from her side to over her head, those deltoids now become the primary movers, while the pecs and lats switch to being antagonists. The third functional muscle group is your synergists, and they help the prime movers usually either by lending them a little extra oomph or by stabilizing joints against dislocation. With all these arm movements, most of the rotator cuff muscles, like the teres minor or the infraspinatus, are acting like synergists. So this is how skeletal muscles are functionally grouped, but what about their actual functions? As individual organs, how do they contract to create both quick and sustained movements and to regulate force? How can Claire's hands gently pet this corgi in one moment and then crush a can in another? I got 2 words for you. Motor units. A motor unit is a group of muscle fibers that all get their signals from the same single motor neuron. Since all those fibers listen to only one neuron, they act together as a unit. In a big power-generating muscle like your rectus femoris in your quad, each of 1,000 or so motor neurons may synapse with and innervate 1,000 muscle fibers. Those 1,000 fibers together form a large motor unit, and big units are typically found in muscles that perform big, not very delicate movements, like walking and squatting and drop kicking. But other muscles, like the ones that control your eyes and fingers, which exert fine motor control, may have just a handful of muscle fibers connected to a single motor neuron. Those relationships are small motor units. And when a motor unit, no matter how large or small, responds to a single action potential, those fibers quickly contract and release in what we call a twitch. And every tiny twitch has 3 distinct phases. To understand which happens when, we gotta go back to the sliding filament model. Immediately after a muscle fiber is stimulated by a nerve, when calcium ions are flooding into into the sarcomeres to pull away those two protein bodyguards of tropomyosin and troponin from the actin, that's called the latent period. The stimulus has arrived, but no force is being produced. That's when the action is just starting. Then comes a brief period of contraction when the myosin heads are binding and pulling and releasing over and over, and the muscle fibers contract. But soon the fiber slides back down into the relaxation period when the calcium gets pumped back into the sarcoplasmic reticulum, and the actin and myosin stop the binding cycle, and the muscle relaxes. Each phase consists of a lot of little steps, and while you couldn't tell by watching my brother dance, the fact is that our muscular movements are pretty smooth. That's because one muscle can produce a variation of smooth forces called graded muscle responses, and they're generally affected by both the frequency and strength with which they're stimulated. So say Claire's trying to lift something heavy, like a paint can. Just as the volume of a sound corresponds to the frequency of action potentials from your ear to your brain, her brain gets her muscles to increase their force by increasing the frequency with which her motor neurons are firing. It's like pushing a button over and over again really fast. Lift! You can do it! Feel the burn! Or whatever. And the faster these nerve impulses fire, the stronger each successive twitch gets, since the muscle doesn't get a chance to relax in between. Because remember, the relaxation period of a twitch is when the calcium is being pumped back into the sarcoplasmic reticulum. If another action potential travels down before that can happen, even more calcium gets released, which ends up exposing more actin for myosin to bind to, and that means more force in that fiber. In this way, twitches end up adding to each other as they get closer together in time, and that's what we call temporal summation. At some point, though, almost all of the actin binding sites are exposed, so all of the myosin heads can work through their cycles of ATP and ADP, and the muscle force can't increase anymore, even with faster action potentials and more calcium. When all those little twitches blend together until they feel like one gigantic contraction, that's called tetanus. At that point, any person on the planet will hit a ceiling of maximum tension. That tension means myosin and the calcium pumps are burning up the muscle cell's ATP, and the finite supply of ATP is what makes it impossible to maintain vigorous muscle activity indefinitely. Prolonged contraction leads to muscle fatigue, and when your muscles just can't take it anymore, all that tension crashes to zero. And remember, all of this twitching happens in individual motor units. Since twitches are driven by action potentials, and action potentials only have one intensity, frequency is the only way to create a grade of force. But when we zoom out to the complete muscle of maybe 1,000 motor units, we can increase the strength of the stimulus by sending action potentials to more motor units. If amping up frequency is like hitting a button again and again, then increasing the signal strength is like smashing the whole keyboard with your forehead. Since multiple action potentials don't travel down all the motor neurons at exactly the same time, each motor unit twitches at slightly different times, which helps smooth out the twitchiness. So contractions intensify as your motor neurons stimulate more and more muscle fibers. This is a process called recruitment, or multiple motor unit summation, and it's where some of your muscles' more nuanced abilities come in. So let's say Claire is holding Abby. She wants to hold on to her tight so that Abby doesn't fall, but not too tight, right? So to increase the contraction force and tighten her grip, she can recruit another motor unit. Recruiting one with 20 fibers will firm her grasp, but calling on one with 1,000 fibers might... well, let's not think about that too much. Lucky for our corgi friend, this recruitment doesn't escalate at random, it follows what's known as a size principle. It starts when the smallest motor units with the smallest fibers are activated by your most excitable neurons, then some larger motor units with larger fibers are enlisted, increasing the strength of contraction. And finally, if you want to give it all you got, which you don't in Abby's case, your largest motor units with your biggest muscle fibers will get involved. These big guns are the last to join up, in part because they're controlled by your largest and least excitable motor neurons. But when they're in, they are all in, packing 50 times the force of those smaller fibers. So the basic rule is the more motor units recruited, the greater the force that's generated. Now that we know how muscle contractions happen, let's look at our two main flavors, isotonic and isometric. Say I want to pick up my crash course mug. I can do this workout myself. If the temporal and recruitment summation triggers enough muscle tension in my arm to overcome the weight of the load and lift the mug, changing the length of the muscles involved during contraction, then that is an isotonic movement. Now if I tried to pick up a building, I could contract my muscles all I wanted and develop a lot of tension without actually changing the muscle's length, in which case I'd be experiencing isometric contractions, and possibly a hernia. Which is why I asked Claire to do all the heavy lifting in this episode. Today, you learned how skeletal muscles work together to create and reverse movements. We also talked about the role size plays in motor units, the three-phase cycle of muscle twitches, and how the strength and frequency of an impulse affects the strength and duration of a contraction. Finally, we discussed summation versus tetanus and isotonic versus isometric movements. No corgis were harmed in the making of this video. Thank you to our headmaster of learning, Thomas Frank, and all of our Patreon patrons who who help make Crash Course possible through their monthly contributions. If you like Crash Course and want to help us keep making videos like this, you can go to patreon.com/crashcourse. Crash Course is filmed at the Dr. Cheryl C. Kinney Crash Course studio. This episode was written by Kathleen Yell, edited by Blake DiPestino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins, the editor is Nicole Sweeney, our sound designer is Michael Ronda, our muscle demonstrations were performed by Claire Grosvenor, and the graphics team is Thought Cafe.